Welcome to This Explainer. Today we are going to unpack the truly invisible threat of air pollution, zooming all the way out to global atmospheric physics and then zooming right back into microscopic engineering solutions. Whether you're deeply embedded in environmental science or just a curious citizen, we're going to take a really close look at how our world handles the delicate balance of the air we literally breathe every single day.
Okay, here's our roadmap for today. We'll be hitting 6 key areas. First, defining the invisible threat. Second, measuring air quality with the AQI. Third, origins and pollutant types. Fourth, meteorology and atmospheric dispersion. Fifth, engineering solutions focusing on the ESP formula. And finally, number 6, wet scrubbers and mechanisms. Let's get right into it.
Section 1. Defining the invisible threat.
To truly grasp how to fight this problem, we first need to anchor ourselves in how the global scientific bodies actually define it. So let's start with the World Health Organization. The WHO defines air pollution quite broadly as the contamination of the indoor or outdoor environment by any chemical, physical, or biological agent that modifies the natural characteristics of the atmosphere. The absolutely key phrase to lock onto here is modifies the natural characteristics. The WHO is looking at the baseline of our atmosphere and pointing out that things like household combustion devices, motor vehicles, industrial facilities, and even natural forest fires are fundamentally altering that baseline chemistry.
But you know what's really interesting? The Environmental Protection Agency pivots slightly here. Their definition focuses much more heavily on the critical threshold of concentration. To the EPA, air pollution is one or more chemicals or substances in high enough concentrations to actually harm humans, animals, vegetation, or materials. They really emphasize that physical conditions, even things like excess heat or noise, can act as pollutants, but only provided they reach that specific, measurable concentration that triggers direct harm.
Moving on to Section 2. Measuring air quality and the AQI.
So, now that we have our foundational definitions, we have to ask ourselves, how do we actually measure and quantify this invisible threat? You step outside, maybe the sky looks a little hazy, but how do we definitively know if the air quality is poor? Well, the answer lies in translating wildly complex atmospheric data into something everyday citizens can actually understand and act upon.
And that brings us to the Air Quality Index, or the AQI. The AQI is essentially a brilliant scheme that distills a totally chaotic mix of individual pollutants, we're talking sulfur dioxide, carbon monoxide, particulate matter, the whole shebang, into a single lucid number. And this number relates directly to health impacts, allowing us to avoid unnecessary exposure. It also serves as a crucial benchmark indicating compliance with national air quality standards, prompting local authorities to take rapid action, guiding broad policy decisions, and ultimately encouraging regular citizens to participate in air quality management.
And you can see exactly how this plays out in the real world. The AQI maps directly to breakpoint concentrations of fine particulates. Just look at the progression here. An AQI of 0 to 50 is categorized as good, which corresponds to very low particulate matter. But as PM10 climbs above 430 micrograms per cubic meter, we hit the severe category, triggering an AQI over 400. Think of this scale as the universal translator between raw, hard atmospheric chemistry and clear public health warnings.
Now, a really crucial point here is understanding what those PM or particulate matter values actually mean. PM10 refers to particles that are less than 10 millionths of a meter in diameter. They are literally invisible to the naked eye. PM 2.5 is even smaller, less than 2.5 micrometers, and it actually makes up about 70% of the total PM10 in our ambient air. Why does that matter? Because these incredibly fine particles are small enough to completely bypass our lungs' natural defenses, lodging deep in our respiratory systems. And the ultra-fine PM 1.0 particles, they are so infinitesimally small they can cross the blood barrier and directly enter the bloodstream. No way around it, that's a serious health concern.
Section 3. Origins and pollutant types.
With our measurement scale set, let's figure out where these microscopic invaders originate. We broadly classify their origins into 2 main categories. First, we have natural sources, which are things like volcanic eruptions, massive dust storms, pollen grains, and natural forest fires. On the flip side, we have anthropogenic, or man-made sources, and these are further broken down into point sources like huge power plants, area sources like widespread residential open burning, and mobile sources like the millions of highway vehicles and railroads constantly on the move.
Beyond origin, there's also a really distinct narrative of direct offenders versus their chemical offspring. Primary pollutants are the materials emitted directly from an identifiable source in their unmodified forms.
Think of carbon monoxide spewing from cars or sulfur dioxide venting from volcanoes. But then we get to the secondary pollutants. These primary pollutants drift up into the atmosphere, interact with one another in the presence of sunlight and natural gases, and essentially spawn entirely new, highly dangerous compounds like ozone and sulfuric acid.
All right, Section 4, Meteorology and Atmospheric Dispersion.
Let's step back for a minute and look at the macro scale. Think of the dispersion of pollutants as a massive, continuous atmospheric tug-of-war. Transport and dilution naturally disperse pollutants, which helps reduce their background concentration. Meanwhile, modification and removal eventually get rid of them through chemical alterations. But, and this is a big but, this entire dispersion process relies completely on climatic conditions: temperature, atmospheric pressure, prevailing winds, and humidity. The atmosphere acts as a giant mixing bowl, and its state ranges from highly turbulent, violent eddies all the way down to periods of total calm where only microscopic molecular movement is happening.
So we generally categorize the weather's impact on this mixing bowl into two groups. First, you've got your primary meteorological parameters. These directly and significantly affect the turbulence level. This includes your wind speed, wind direction, temperature, atmospheric stability, and the mixing height. Then we have the secondary meteorological parameters, which are things like humidity, solar radiation, atmospheric pressure, and even the physical topography of the land below. Basically, these secondary parameters are the puppet masters. They dictate and influence exactly how those primary parameters are going to behave.
When we talk about mixing, turbulence is essentially the atmosphere's giant blender, and it comes in two flavors. Mechanical turbulence happens when wind blows over uneven ground, which physically causes the air to become gusty, actively forcing pollutants to mix with clean air. Thermal turbulence, on the other hand, happens when the ground heats the air right above it, causing bubbles of warm air to aggressively rise. These rising thermal eddies literally carry pollutants higher into the atmosphere, spreading them out over massive distances.
Now, as these thermal bubbles and the pollutants trapped inside them rise, they start to cool down. This cooling process is governed by what we call lapse rates, which are absolutely essential concepts to lock down. First is the dry adiabatic lapse rate, or DALR. This is the rate at which completely dry air cools as it rises, which is exactly 9.8 degrees Celsius per 1,000 meters. Next is the wet adiabatic lapse rate, or WALR. This is for saturated air, and it cools much slower, usually around 5.6 degrees Celsius per 1,000 meters. And finally, we have the process lapse rate, or PLR. This is the specific cooling rate of a rising puff of flue gas pollutants. Because this puff is incredibly complex, neither completely dry nor completely saturated, its PLR sits right between the DALR and the WALR. Let's bring it back down to earth with Section 5, Engineering Solutions in the ESP Formula.
Now that we understand the vast, chaotic, natural forces at play, let's shrink our focus back down to how human engineering actively fights back. Our control devices deploy a truly fascinating arsenal of physics. For particulate control, engineers harness gravity settling, centrifugal forces, filtration, scrubbing, and electrostatic forces. To control gaseous pollutants, which are significantly trickier to capture, we use chemical absorption, physical absorption, extreme high-heat combustion, and masking.
The absolute crown jewel of particulate control is the electrostatic precipitator, or the ESP. It essentially charges particles and magnetically pulls them right out of the air. And the whole thing is governed mathematically by this incredibly elegant formula, the Deutsch-Anderson equation. Let's really look at what these symbols actually mean.
Let's unpack this formula because it's brilliant. That strange N symbol, eta, represents the fractional collection efficiency. That is our ultimate goal, the grade we want to maximize. AC is the total physical area of the collection electrode plates. VPM is the particle migration velocity. Simply put, how fast the particles are pulled toward the plates by the electric field. And Q is the volumetric flow rate of the gas aggressively passing through the system. Now, to make this math work, the equation operates on a few key assumptions. Gas velocity is assumed uniform, particles are fully charged, and we completely neglect the repulsion effect between the particles themselves.
Okay, let's actually solve an example together, right now, to really see the engineering trade-offs mathematically. Let's imagine a small factory stack. The particles move toward our plates at a migration velocity, VPM, of 0.1 meters per second. We have built a collection area, AC, of 100 square meters, and the factory is pushing gas through at a flow rate, Q, of 10 cubic meters per second. Let's do the math. First, we multiply our velocity of 0.1 by our area of 100. That gives us exactly 10. Next, we divide by our gas flow rate, which is also 10. So 10 divided by 10 is simply 1. Now we plug that 1 into the rest of the formula. Eta equals 1 minus the exponential of -1. The mathematical constant e to the power of -1 is about 0.368. Subtract that from 1, and you get 0.632. So, what does that mean in the real world? It means our electrostatic precipitator has a collection efficiency of exactly 63.2%. Here is the absolutely crucial engineering takeaway. If we want to push that efficiency closer to 100%, the math tells us we only have two physical choices: slow down the gas flow rate so the denominator shrinks, or spend the big bucks to build much larger collection plates to drive up that area numerator. It is a literal balancing act of physics and economics.
Finally, Section 6, Wet Scrubbers and Mechanisms. Our final engineering marvel handles both particulates and dangerous gases simultaneously. Wet scrubbers operate in three really beautiful, distinct steps. Step 1 is gas humidification. This conditions those ultrafine particles we talked about earlier, forcing them to swell and increase their size so they're easier to catch. Step 2 is gas-liquid contact, which is the most critical factor. This is where those swollen particulates violently collide with water droplets to form sticky agglomerates. Finally, step 3 is gas-liquid separation, where these large, heavy agglomerates settle out of the gas stream entirely, leaving mostly clean air to exit the stack. By fully understanding the vast natural forces of dispersion and then deploying brilliant mathematical engineering like scrubbers and precipitators, we can actually fight back against atmospheric contamination. But it leaves us with one final, very provocative question. As our global industries and populations continue to grow exponentially, will our mathematical and engineering ingenuity keep pace, or will this invisible threat eventually outscale our best possible solutions? Something to think about. Thanks for joining me on this explainer.